Alright guys, so what we're going to do today is talk about optimization problems. This is like the core of calculus. And we're going to do this one, a farmer has 800 meters of fencing. Okay, and wants to fence a field. One side of the field is the river. So let's just draw it. Instead of writing out the question, I'm just going to draw you a picture. One side of the field is the river. What dimensions give the largest area? So you have two widths and you have a length. And they're telling us that in terms of fencing, all they have is 800 meters. And here's our river. I'll do a couple more waves for you guys. We know that area equals length times width. And perimeter would be 800 equals length plus 2 width. And what happens essentially is I could isolate for L. And how I do that is L equals 800 minus 2W. And I can sub that in there. So A equals 800 minus 2W times W. So what I have is 800 W minus 2W squared. Now, if we're trying to maximize this is area. So I want to sub into the function I'm trying to maximize, which is area in this case. If I take the derivative of that, so now that we have W, the maximum amount that W can be, like logically speaking, is that W has to be between 0 and 400. And why is that? It's because even if the length is 0, then the biggest W you could have, 800 divided by 2 is 400. So you have to set your own bounds, basically. You can't just say any value. And how you do that is just understanding what the problem's asking. If there's only 800 meters of fencing, assuming we have no length at all, the largest width you could have is 400. So that is our interval that we're in. Now that we have the derivative, I have to take the derivative of this, which is 800 minus 4W. So I get W equals 200 as critical point. That's when A prime equals 0. So I test those points. I go A at 0, A at 200, and then A at 400. I get a variety of points. A at 0 is 0. This one's, 80K. This one's 0. And so clearly there's a clear banger winner here, which is 200. So the maximum area is 80K. The max area is 80K meters squared. That's already halfway done no. Let's say that we have a cylinder here. If we have, this is the last example. So if we have 300 centimeters squared of tin to work with, to make the biggest, most awesome soup ever, how much soup could you hold? You have that much tin to work with. So if you have this, then it's a cylinder. And volume of the cylinder is pi r squared h, because pi r squared is the area of the circle and h is the height. And then surface area is pi r squared plus pi r squared plus 2 pi r h equals 300. And now we really just simplify to 2 pi r squared plus 2 pi r h equals 300. So then what I could do is isolate for h. And this one, that would be 300 minus 2 pi r squared divided by 2 pi r. All that equals h. If I sub that in, then v equals pi r squared times 300 minus 2 pi r squared over 2 pi r. And that actually can be simplified into pi r squared times 150 pi r minus r. And if you were to FOIL that in, I'd actually have 150 r minus pi r cubed. So we got to know our bounds again. So essentially, we have 300 centimeters squared of 10. So that means 2 pi r squared, which is the two faces, have to be, your 2 pi r squared has to be less than or equal to 300. So your two circular, assuming you have no height at all, and you're trying to maximize, because we have only r's now, right? So we're trying to find the bounds for r. So r must be less than or equal to the square root of 150 over pi, essentially, if you divide both sides by 2 and then square root both sides. So really, your range is between 0, r, and then this value. So let me just write that right there. So you just have 0, like that. So then, what happens is we just test the values. So we find the critical points right here, because v prime would be 150, and then minus 3 pi r squared. So if I were to solve, I'd get the critical number of r equals root 50 over pi. This is getting really messy, but it seems like when we test, you would test all these, test this point, and this point into the original. And it seems like when we put v of root 50 over pi, we get 399 centimeter cubed, which is the maximum volume. So I'm sorry it got a little bit messy there, but I hope you guys got the main idea. But there's a general strategy, so you want to find the quantity that's trying to be like maximized or minimized. And what's going to happen after that is you want to see that one variable that's in that equation and determine the bounds based on that. So at this point we had r's left, right? So you want to see the bounds based on r. And then you want to find the global max or global min by kind of do like a first derivative test kind of vibe. Not first derivative test, but basically find the critical points and testing all the endpoints, the critical points, to see which one gives you the highest or lowest value. So that basically sums up optimization. Just want to see what the next is on related rates, which is quite a beast in itself, but we'll be going through problems like that as well. Cool.